Hi everyone, today I will talk to you about a topic which is beyond our nano manufacturing course but is well related to it. This topic is IC design process. Okay, I want to introduce myself to you first. I am Ahmed Gharib from Egypt. I graduated from Faculty of Engineering, Department of Communications and Electronics, and this was my graduation project. As you see, this address CMOS LTE receiver IC design may be not obvious to you, but I want to make it more obvious because I will use this project as an example during this presentation. Okay, CMOS is a semiconductor device which we used in our project. LTE is a standard for what we have did in our project, and the receiver is the thing, as you see, the thing that we designed. Okay, here's the contents. First, I will talk to you about what is the difference between analog design and digital design, and as you will see, this project is about analog IC design, and then I will talk to you about analog IC design flow, and then system level design highlights, and then circuit level design and layout highlights. What's IC designing? As you have learned in our nano manufacturing course, we use semiconductors to create end user device. But what the designer seeks is to see what users want and try to make an optimum design using the technologies available in the nano manufacturing field. He creates something that can be done in the industry. Okay, and then why analog? Why still there is analog today? And maybe you think that everything today is digital. Yes, everything depends on digital, but everything depends on analog as well, because life is analog. Because when you speak into your mobile phone, this voice is analog, and your mobile phone has to translate it to convert it to digital signal. And for this, for example, there is something like analog to digital converters, and this is done by analog design. Okay, analog design versus digital design. What is the difference? Why some people prefer to work on analog design and some people prefer to work in digital design process? Okay, I'll start with digital design process. In digital design process, we use some languages, something like a programming language, maybe VHDL, maybe something like Verilog. Those languages we use to create a system, to design a system, and this system is auto-generated into circuits, and then you do some simulations, and then this is auto-generated to the circuit layout. Later in this presentation I will tell you what is layout. Okay, but in analog design process, when we have the specifications we want to match, we start our system design, and then we do our circuit design. We put every single transistor in its place on the circuit by ourselves, not through an auto generation or something like that. We start to design the components, we start to simulate the circuits, and see what is the worst cases, the corners, and then we make a system simulation. We see also what is the worst cases in the system simulation. We make the layout design by ourselves, and till the end of the debugging of our design. Okay then, so what's the analog IC design flow? We first start to brainstorm for ideas for the device we want to make, we want to create, and then we start creating our block diagram, which we put every block connected to the other blocks in a design that gives us the function we want to perform. Then we go to the next level, to the next deeper level, and we start to put our components in the scope of our design. We start to make a component level circuit design. We put every transistor, every resistor, every capacitor in this design, and then we start to make our simulations to see how the output is, how does it match what we seek, and after that we go to the physical layout design, which is then sent to the manufacturer, who starts to work on it. Okay then, after that there is the IC fabrication, there is the packaging, there is debugging, there is making some prototyping to test and characterize, and then we put it into evaluation boards to test it again, and then we create our products. Let's look more deeper into the IC design flow. We first start by the system architecture concept review. We start to think about how this system works, what is the concepts of its work, of relating its blocks to each other, and then we study our standards, or our specific standards that we will match for our design, for our device we make. Standards, of course, are made internationally. You'll see something like LTE, maybe you have heard about it. And this standard obligates the designer to some levels of quality or some levels of performance that they must be obligated to it. And then you do some system review. You see how your system as a whole works, and then you go to think about the blocks, how the blocks work together, and study the concept well, and then start designing your blocks. And after this designing process, you start to adjust your blocks with each other, adjust your design so that all the blocks can work with each other. And then you go to the circuit level review, where you look to your circuit as a combination of transistors and capacitors and semiconductor and resistors, and then you start designing. your circuits. Of course, that's for making a match to the specifications. You go from the higher levels to the lower levels, and all you want to do is to make the design you seek with the performance you seek and match your standards. And then you start your layout process and go for your final review before the system integration. And then we go to some system level design highlights. We in our graduation project, as an example, have made a receiver that obligates to the LTE standards. And this receiver has a system design, a block diagram like what you see. It has many blocks starting from the antenna that receives the signal, passing through the low noise amplifier and the other components. For our system level design, here is the specifications mentioned in the standard, the LTE standard, that we have to obligate to it. We have got these specifications to be our guide in our design. Then we look at the contribution of every block in these specifications we mentioned. For example, this is the noise contribution, and we have the low noise amplifier, which is a block of the receiver. This low noise amplifier has a noise contribution with 4% of the total noise of the receiver. Of course, 4% is a little percent, and this is why it's called low noise amplifier. Here is the low noise amplifier in our system design on our block diagram, and from these specifications we derived specifications related to this block, to this low noise amplifier block, and then we go to start working to match these specifications. When we started to think about the circuit design, the circuit level design, we found that there is many topologies, and every topology has some characteristics. There is the common source topology, the common gate, the GN positive common gate topology, and every topology has benefits and have advantages and disadvantages. We start to make our decisions about this topologies and choose one topology that will best fit the standard we seek. And as you see, this is the proposed topology, the topology that we choose from the previous 3 topologies we studied, and we found this is the best topology we can make. And as you see here, there is resistors in the circuit level, and coils, and capacitors, and transistors. This is a circuit level design which depends on components on it. Then we start making our simulation. We start seeing what the results will be using some simulation programs, some simulation tools. This was made with Cadence. It's a very powerful tool for analog IC design, and we have put our components on the design and started to make our simulation. Here's the ADC simulation. You can see from the voltages and currents at every point. And here is another simulation which is simulating the gain here on the y-axis related to the frequency on the x-axis, and there is the noise figure also related to the frequency, and we make then a summary from this simulation results and see how we reached the seeked specifications or not. We mention every specification, and we mention what we reached through our simulation, and we find that we somehow near to the specifications required, or better sometimes, worse sometimes. And of course, after a table like that, we go back again to our schematic diagram and see if we need to make some modifications to make it better, to have a better result, to have a better obligation to the specifications. And here we go, we reach our layout, the final step. And the layout is something that the manufacturer will understand, will take it from me and put it into the machine somehow, and the machine will start working on it. And in this layout we draw in a lower level design, we draw our N regions and B regions, we draw our metal contacts, we draw our poly silicon regions, and using the tool, the appropriate tool, we make this design and send it to the manufacturer. And what is a layout? A layout is just if we have some schematic diagram like that, where we have transistors, it makes a layout like that, where we have our metal contacts, this point F is this point F, our this point E is this point E, this is the metal contact, and we have our gates. If we have this in M2, this gate, this gate, it's here. Thank you. I hope you have got some benefit from this little overview of very little overview of IC design, analog IC design. And finally, I wish to thank Professor Anish for this great course that I have gained a lot of benefit and a lot of joy from it. Thank you again.